compared bromine to sulfur? Yeah, so I can't compare chlorine to oxygen. That would not be possible on a final. You have to go along the left and down diagonal. Okay? Yes. Partial pressure, do you have one for me? Okay, do you want to find one and get back to me? Yes. Fall, what year? Fall 2008. Let me find that. Number 8. This one. Is that right? What's the dipole moment? Dipole moment means the same as having a dipole. It means the same as something being polar. So you're looking for the one that the smallest dipole moment possible would be something that's non-polar. Yeah. So let me just do this really quickly with you. Ideally, you write out the electron configuration, the Lewis structure for all of these. You'll find out this one's bent, so it's polar. You'll find out that this one's non-polar, and it's the correct answer, because both carbons are tested equal. You'll find out that this, the center of sulfur, is tetrahedral, but those hydrogens make it polar. You'll find out, well, this is just C and O, it has to be polar. And then this, because of the chlorine, has to be polar. Yes?
On question 23 for the final review, it's filling out a table for molecules, and one of the things it asks is the oxidation state.
Yeah, can you give me a molecule?
ClF3.
ClF3.
Yeah.
I think this one's T-shaped, is that right?
Yeah.
Okay. Well, actually it doesn't matter for oxidation state. So for oxidation state, let me refer you, because people get tripped up here, and all of you should be aware of this. In your reader, I'm going to go to chapter 3 and show you my flow chart from there. On page 20, this flow chart right here, when you're doing oxidation state, you'll have to go in this order. So you cannot skip a box. Be really careful of that, because you can get the wrong answer if you do. If you go down in order, it's not elemental state, but you're going to find out chlorine pretty much always -1. So that then dictates this has to be -1. And thus, by default, this now is +3. Okay, do you have another one?
Well, it says that the total oxidation state is -1 for that model, though. So why is that?
Can I see it? I don't think I have that handout with me. Pass it on over. The oxidation state for the underlying element, which is the fluorine. Yeah. So on the same as of this final coming up, we're going to do it for the underlying elements. So be really careful. Good. Next. Yes. Oh, hold up. You walk all the way back down here. Fall 08, what number? 24? Okay, what part? What's that? Oh, the whole. Two-pack likes these kind of questions. This is 24 following. Right? Okay. So he gave me CH4 and C2H4. And there was a hint, and this hint is actually really important. Write and balance the chemical reaction for each of these. They're both undergoing combustion. So you kind of had to do this part first. I'll just write it out for you. Is it okay if I just write it and balance it? Okay. So if you didn't do this, you weren't going to get the answer. So you had to write a combustion, balance this all out. Okay. It says a 5-gram sample So, and it's a mixture of both these, so both of these are 5 grams. Is that okay? 5-gram sample was burned in oxygen, yielding 14.5 grams of CO2. Both of these add up to 14.5 grams. Okay? And some water as products. What's the mass percent of sample that was ethylene? So that's the one I'll put the star by right there. Write balance this first to figure out what the heck you're doing. Okay. So there could be a couple different ways that you might get to the answer. You may or may not follow exactly the way they solved it here. But basically, if you say, let me get a different color here, and let me at least set it up for you, and I probably won't solve all of it, just so we have enough time, okay? But you can call this one, say, let's say we have X grams of this and Y of this. So the ethylene, which is the one you want, is 5 minus X, okay? And the methane is X. So then, you could say there's X moles of CH4. Is that all right? Because I just said it was X. Or X grams, I guess. And then you can go through a little kind of conversion process. We do use the molar mass of CH4, which I think is around 16 grams per mole. And then you can say, well, there's 1 mole of CO2 in its own reaction for every 1 mole of CH4. And then do a little conversion. There's 44 grams per mole of CO2. This is a little different than the way you see the answer key solve it. Okay. And this will be grams of CO2. Is that all right? Then I'm going to do an alternate, different color calculation here for C2H4, the ethylene. But this one is 5 minus X. 24 and 4, that's 28, I think, grams per mole of ethylene from the periodic table. There's 2 moles of CO2 for every 1 mole of C2H4. And then it's still 44 grams per mole. Is that okay? Okay. Now this is the sum grams of CO2. Now let's get a different color. That number plus that number equals 14.5. So now I have 2 equations and 1 unknown X. Is that all right? Or really, I guess, 1 equation right here with an X in it. Solve for X, and you're pretty much there. Is that kind of okay? Okay, cool. Next. If it's asking if we had a molecule that had something with 3p to make a pi bond, you wouldn't see that on the front. But yes, it would involve the 3p's. Okay, yes. Fall 09. Fall 09. By the way, I'm going to attempt to get this all posted if there's no technical difficulties by Monday. Okay, so sometime tomorrow. What number did you say? 30. This one right here. Okay, 5 and 6. Okay, 5, 6, 7, 8, 9, 10. Okay, so this, everything that's not highlighted, or that's highlighted is what you're putting for your answer. And they're curious about 5, 6, 7, 8, 9, 10. That's the 2p. So for 2p, anybody, what's n? 2. What's L for p? 1. So that's why you see 5, 6, 7, 8, 9 all have 2's, and they're all 1's here. Is that okay so far? And then if L is 1, is it okay that M spells 0 plus 1 or minus 1? Yes. Okay. So thus you see the 0's, the plus 1's, and the minus 1's. And then for both 0's, there's a plus 1/2 and minus 1/2. Is that okay so far? Now, why is it this order is your next question. That that we did not grade down on what order you put them in for 5 through 9. That's right, yeah. 5 through 10. So, as long as you had all of those 6 sets of quantum numbers correctly listed horizontally, the vertical did not matter. Okay, next. Non-ideal, anything in particular? In the real gas law, the Van der Waals. Okay. We're going to do something quick on Van der Waals. It's more of a general question, but just to make sure you all got it, just in case you do see a question. This is chapter 6 in the middle. Just so you understand this equation right here. Okay, it's almost PV equals nRT. There's a couple extra terms. First, A and B are constants. You would know that you're going to use this equation if we give you A and B. Right? Or somehow you know it's a non-ideal. But even if you figure it out as non-ideal, you still need A and B if in the scenario of a final. Okay? The n squared A over B squared, that's the pressure correction. And the NB is the volume pressure. Where does that come from? NB comes from the assumption that breaks down, which says that all the volume of gases are 0, meaning they're tiny, so that they take up no volume. That assumption breaks down to the real gas. Well, how about the n squared A over B? There's a couple different assumptions that are attached to that one, which I list one of them, I guess, here under the pressure correction, and that is that molecules are attracted to each other. So assuming there's attraction, you're going to have that term there. And that's purely conceptual. Next.
Winter 2010, number 23, A, B, and C.
Oh, hold up. That was too much information at once. Winter 10. Wait. I didn't give you a winter 10. Did I?
I found a practice exam.
Final exam?
Oh, final exam? I think
No.
I'm looking at the midterm. Hold on.
Okay, exam 1 or 2?
Exam 2.
Exam 2, winter 10.
Number 23.
23. Hold up, looking for it. Okay, this one. Right?
Yeah.
Okay. A valve connects to reaction gases. Okay. This is kind of a Dalton's law question with a little bit of a twist. Okay? Let me try this and get a blank page out here. Okay. Zoom out. We've got nitrogen and oxygen. The valve is open, these two react, the reaction occurs. Okay, assuming the reaction takes place at 25 degrees C. What's the limiting reactant? Okay, you know, even if we didn't use those words, we have information leading to moles. So what you're going to do for part A is, I'm just going to talk it through, and you can find the answers in the reader. What you're going to do to find the limiting reactant, you need moles, but in this case, because you're given gas information, you're going to use this. So you've got a P, a B, and a T. R is a constant. Just make sure to change the pressure to
ATM.
ATMs, okay? So use this equation. You're going to find moles for both. The one that's a smaller answer is your limiting reactant. Well, you're going to get N2 and O2. You need to convert eventually to N2O. So make sure and balance this. Let's see, if I balance this, I guess I put a 2 here and a 2 here. So this will ultimately get you to the moles of N2 and the moles of O2. You're going to use that to convert for both cases to the moles of N2O using stoichiometry. So the only difference between what you saw in chapter 4 is usually we give you the moles of N2 and O2. But here we're having to calculate it and then do it. Okay? So that's the first step. You want to do part B also?
Yeah.
Part B says how many moles of the excess reagent remain. So the answer from part A is nitrogen is a limiting reactant. So the way I set these up, remember this is going to be your limiting right here, the one I have underlined. So you start with your moles of the correct answer, and then you do a molar ratio to go to your excess. So you say 2 moles of O2 for every 2 moles of N2O, and then you go to the molar mass, and this is going to be the actual amount used. You subtract it from the amount given, and that'll be your excess. Is that kind of okay?
Yeah.
Okay, for part, did you want to do part C? You did? Okay. Part C, what is the pressure of N2O form? So we want the pressure of N2O. Okay, so let's see what we have. The pressure of N2O. So I'm thinking the ideal gas law. There's my ideal gas law. Let's see what I have. First, I have temperature. Check. That's 25 degrees C. I change it to Kelvin. I have the ideal gas law constant. That's cool. Volume is the sum of these two numbers because the valve is open. So it's the sum of this and this. Now, N is the tricky one. N, let's zoom out a little bit. N is actually the correct answer from the limiting reactant part. So I go back, whoa, that was unfortunate. I go back here, which you can't see, but I'm pointing at the answer. I wish you could see it. But it's literally right here where my pen is. If you could see it, you'd be shocked. Oh, okay. It's right there. So what I underline. Is that all right? And then, is that the last part? What's the total pressure as the answer? The total pressure is what's left over. So the N2 is limiting, it's gone. So it's this, which you just found. Is that okay? And then, using the moles of this that was left over from part B, I think, you use the ideal gas law to change that to pressure. And you sum these two. Sorry that was fast, I just want to get to everything. Okay, yes? Fall 8 for the finals now, I assume. Fall 8, number 3. This one? Okay. So there's 2 ways you can do this problem. On the final, I lost where you went, but on the final, we're going to give you the electronegativities. And they're going to be in the periodic table. Did I close the last 2 pages of the final yet? Oh, I did? Okay, so it's in there. So all you need to do is subtract the numbers for each element. And the most ionic would have the largest difference. If you ask you the most covalent, you look for the one with the smallest difference. That's it. Next. Yes. Number 9. Oh, this is a collaborative question. Number 9. So what problem do we have following part?
What's really good session?
Actually, we want to show you athletes. All right. I think I'll take one or two more questions. Yes. Fall 2008. Let me find it first. Oh, it's right here. Okay. 28. Who's Clark? All of it. Okay, let me walk you through this part just from here. The chromium is +3 here. Chromium is +3 here. Okay. But here it's +6. So is that okay? Oh, okay. I thought you said all of it. So starting at part B. Part D. So you're okay with parts B and C? Okay. If it's just part D, no fear. All you're going to do is look at the electrons. 12 here and 6 there. Those two have to match. So you're going to multiply this reaction by 2. So this part of the reaction is a double. That's why there's 2 chromates here. And there's going to end up being 28 of these to subtract off from 12 of these. And then there's going to be, likewise, I mean, there's going to be 4 of these. That's why there's 4 here. And there's going to be 14 of these in the acidic conditions. And then you find the total number of H pluses. So if there's 28 here and 12 here, 28 minus 12, 16. You're going to add 16 OH minuses to both sides. Okay, ask me after we got more. I'm going to take one last question. I'll go back to that. Last question, yes. You're the winner. 27 of fall 2009. Fall 9. Was there a fall 9? Oh yeah. You said 27? Is this the balloon problem? The balloon problem? Okay. Alright, this will be the last one. Okay, we have a balloon. What page 185? Alright. This balloon is filled with nitrogen dioxide. Initial volume, V1, is 1.20 liters. The nitrogen dioxide reacts, oh my, NO2 reacts to form dinitrogen tetroxide. That's that. Better balance it. There we go, it's balanced. The temperature and pressure remain the same. What is the final volume after the reaction is complete? Okay. So if I'm thinking of gas laws and all that action here, remember I use the combined gas law. And I'm using this because I'm seeing things are changing. When things are changing, I'm thinking the combined gas law. Now they tell me in the question that pressure and temperature don't change at all. So I'm going to ignore that. And so what's left? Well, all that's left is V1 over N1 equals V2 over N2. And I asked myself, I made sure, was volume changing? Yes, that's what it asked me about. Are moles changing? Yeah, there's a reaction going on, so moles are changing too. Okay? Let me zoom out a little bit. Okay, so I know V1. V2 is what I'm asked about. Is that okay? Okay. Now N1 and N2 are a little bit trickier. N1, let's do it like this. Okay, I don't want this. Okay, there we go. Okay, initially, there's a certain amount of moles of this, but we don't know how much. So what's your favorite variable? Your favorite letter? Okay, that's cool. X, all right? And initially, there's none of that. Is that okay? It tells me it's all this. Okay, then this thing reacts, okay? And it tells me it reacts. It says 2/3 of the nitrogen dioxide react to form the dimer. So I react 2/3 of X away, and I'm left with 1/3. Does that make any sense whatsoever for the left-hand side? Because it says 2/3 react, so that must be what's gone. I'm left with 1/3. Okay, just by simple math. Okay. So now, let's see. Let's do it this way. I have 1/3 of this left over. 1/3. No, let's do it like this. Let's do it like this. 2/3 X of the N2O react. Is that okay?
Yeah.
That's what I said in the problem. So, and we're assuming these are moles. So now let's do a mole ratio. There's 1 mole of N2O4 for every 2 moles of NO2. Oops, NO2, is that okay? So what's left? 2/3 by 2, that's 1/3 moles of N2O4, our generator. And I mean the X carries over to the X. Is that okay? All right. So, okay, here we go. Let's try this. What is, I'll try to show the whole page here. What is anybody N1? Yes, nice. X. Exactly, sorry. X. Okay. Let's go a little crazy in the head here. What is N2? It's not just 1/3. It's the total moles left over at the end. What is the total moles? It's more than 1/3. 2/3. Yeah, they're both left over, right? So this is 2/3 X. There's 1/3 and 1/3. This is left over, and this is created. The product is created, the reactant is left over unreacted. Full of 2/3. So now the X will drop out and you can solve your answer. Okay? Cool. Okay, I'm going to stop right there.